Hi, my name is Mahi, and I will be presenting the paper titled People Adjust Recency Adaptively to Environment Structure, which I worked on alongside my advisor Peter Todd. People often make decisions from a small sample of recent events. That is, they often use recency in decision making. One demonstration of recency is in the hot hand phenomenon. For instance, people often predict that a basketball player will make a shot if they made a shot recently, and people make such predictions even when consecutive events are independent. For instance, Wilkie and Barrett found evidence for the hot hand phenomenon even with coin tosses. Another demonstration of recency is in the description experience gap. Researchers find that people are more likely to undermine rare events when making decisions from experience, for instance, when they're repeatedly playing with slot machines, than when they make decisions from a description of their odds of winning. One explanation for this description experience gap is that decisions from experience are susceptible to recency effects, and that rare events are less likely to be part of that small sample of recent experience and are hence undermined. Today, we focus on why people's decisions are influenced by recency in such a way. And we compare two possible explanations. One, that it is a default decision strategy adapted to real world environments. And two, that it is a product of cognitive limitations. So let's focus on that first explanation, that recency is a default decision strategy. This is based on the idea that many real world environments are dynamic and autocorrelated. An example of this is the fertility of food patches, which changes across time. Cultural environments also tend to show these characteristics. For instance, the importance of news events and the occurrence of words and phrases in speech are also autocorrelated across time and change with the passage of time. In such environments, recency is an effective decision strategy. Here, a small number of recent events are most representative of the current state of the world, and therefore it just makes sense to make decisions based on recent experience. Another explanation for recency suggests that it is a product of working memory limitations. We can manipulate only limited amounts of information at a time, and thus the working memory capacity might be limiting the backlog of information that is included in decisions. We do recognize there are two explanations for recency, that it is a decision strategy and that it is a product of working memory limitations, might not be mutually exclusive. That is, it is possible that both are responsible for recency in decision making. For instance, if the optimal sample size of information to be included in a decision is smaller than the working memory capacity, people might be actively strategizing to employ recency in those cases. However, at other times, when the optimal sample size of recent information that has to be included in a decision is larger than the working memory capacity, or when people are mentally overloaded, recency might be a product of working memory limitations. We investigated both these explanations by collecting data of participants performing a decision task called the probability learning task. Here, participants were presented with two light bulbs, and across a sequence of trials, they had to predict which of the two light bulbs would turn on. Each bulb had some underlying probability of turning on, which was determined by us beforehand. Here's a quick demonstration of the task. Here, the participant chooses bulb B. It turns on, so they win a game point. They choose bulb B again, and this time bulb A turns on, so they lose a game point, and the trials go on and on. The reason why we chose this task is because it has a large literature. Therefore, there have been many studies on this task before, so we had a strong backbone to rely on. Also, we believe that this task is ecologically valid. Many real-world decisions ultimately boil down to two alternatives. For instance, deciding whether to talk or not to talk, to eat or not to eat, to do something or not to do something. In our experiment, the probabilities of these light bulbs did not remain constant across trials. In fact, they varied across trials depending on the decision task structures that participants were given. Totally, we had 3 decision task structures in our experiment. In the static task structure, the probabilities remained constant across trials. In the gradual shift structure, the probabilities changed gradually across trials. So initially, light bulb A might be probable, which would then gradually change to a high probability light bulb B, and it would move back and forth slowly. Finally, in the sudden shift task structure, the probabilities of the light bulbs changed abruptly. Therefore, here light bulbs A and B changed in probability at spaced but varying points in time. We chose these three task structures because the best performing degree of recency varied across them. We have simulation results to back this up. We conducted simulations to see how well different recency parameters performed on these task structures. Here, on the x-axis is recency and on the y-axis is decision performance. And we can see from these simulation results that in the static environment, a low recency is most optimal. On the other hand, in the gradual environment, a higher recency is most optimal. Finally, in a static environment, an even higher recency is most optimal. These differences in optimal recency values across these decision task structures allows us to test for explanation 1 of recency, which is that people are using recency because it is an adaptive decision strategy. We expect that if it is a decision strategy, participants will flexibly adjust their recency values to match the optimal recency values for their task structure. Therefore, we would expect them to show optimal patterns of recency across the task structures. In addition to the decision task, we also gave participants 4 working memory tasks. These include the digit span, the operation span, visual array, and the spatial span task. Measuring working memory helps us test for explanation 2, which is that people use recency because of working memory limitations. This hypothesis will be supported if lower working memory scores correspond to a higher use of recency. That is, if working memory scores and recency are negatively correlated. Some more details about our methods. We had a between groups design, so each participant did only one type of task structure. The number of participants was 48, 31, and 34 across the task structures. Another important thing to note is that static task structure had only 100 trials, while the other two had 200 trials. This is because data from the static task structure was taken from a previous experiment, and in that experiment, our number of trials was lower. Across all 3 task structures, the underlying probabilities of light bulbs varied between 0.8 and 0.2. Data collected from participants was then fit with a recency model to determine how much recency they were employing in their decision making in the experiment. The recency model we used assumes that participants discount older outcomes when calculating the value of light bulbs at every trial. Here is the formula. This R parameter is the recency parameter and was fit using Bayesian hierarchical modeling to each participant. Essentially, what is important to know is that higher R means greater recency and means greater discounting of older outcomes. R varied between 0 and 1. Therefore, when R was equal to 0, it would suggest that participants were doing equal averaging. That is, they were not discounting any of the older outcomes. When R is greater than 0, it suggests that participants were doing some kind of recency-weighted averaging, therefore they were discounting older outcomes. And finally, when R is equal to 1, it suggests that participants were doing extreme recency and were only considering the very last outcome in their decision making. Now I will show some plots of the model fits. This is the data of a single participant, and the dots indicate the decisions that the participant made, light bulb B or A, and it seems like initially this participant is choosing B, light bulb B often, and then moves to A and moves back and forth. And this is because this is a sudden change trial. And this dotted line shows the underlying probabilities that this participant was given. This red line shows the fits of the recency model, and as you can see, it fits the participant's data pretty well. This blue line out here is the fit of a simple Bernoulli baseline model that we used for comparison. This baseline model had only one parameter, which was the probability of choosing light bulb A or B. Here is the data of the other participants in the other task structures. And as you can see, the recency model seems to be fitting the participants' data pretty well. Overall, the recency model fit 95 participants better than the baseline model, whereas the baseline model only fit 18 participants better. The recency parameter, which was measured for each participant, was then used in later analyses to investigate our 2 explanations for recency. For our first analysis, we tested the first explanation by investigating whether participants adapt recency to task structure. As you might recall, we conducted simulations showing that the optimal recency parameter differed across task structures, and if participants are adaptively using recency, then their degree of recency should vary across task structures, tracking these optimal values. That is, their recency should be lowest for static, higher for gradual, and highest for sudden. In our results, this is exactly what we found. Here the different box plots represent different task structures, and on the y-axis we have recency. And as we can see, recency is lowest for static, higher for gradual, and highest for sudden. Next, we asked whether this recency was learned with task experience. That is, whether participants were able to adjust recency across trials as they gain experience with the task. We're wondering if participants tended to start task structures with similar recency values, which they then altered across trials as they gained experience with the task. To study this, we split each experiment into 50 trial phases. For instance, here is the data of a participant across all 200 trials, and we split it into 50 trial phases. We then fit a different recency parameter to each phase. We were interested in seeing how this recency parameter changed as the trials went on. And here are the results. On the x-axis, we have the trial phase, and on the y-axis, we have recency. As you might recall, the static task structure had 100 trials only, and therefore this line is shorter. Overall, we find that participants start with similar recency values across all 3 task structures, which they then change as the trial phases go on. In the gradual and sudden task structures, the recency values become more optimal across time. On the other hand, in the static task structure, the recency does not seem to be changing a whole lot. We believe that this might be because since the static task structure had fewer trials, participants did not have enough trials to change their recency. Or it might be because in the static task structure, a lower recency was most optimal. And such a low recency might be very taxing to participants since it involves using a larger number of previous outcomes, and hence it did not change a whole lot. However, overall, we do believe that our results show that people flexibly use recency as a decision strategy. They seem to be changing the recency parameter across task structures and adapting it as they gain experience with the task. Finally, we were interested in this default starting recency value. We were curious about why participants tended to start with this recency value across all 3 task structures. And in order to study the starting value, we conducted more simulations. We conducted simulations to compare performance of different recency parameters, and we aggregated this performance across 3 task structures and all probability contingencies from 0 to 1. And here are the results. Here on the x-axis, we have recency, and on the y-axis, we have decision performance of the different recency values aggregated across various task structures and probability contingencies. And as you can see, the highest decision performance is achieved at around a recency of 0.6. Here is the default recency that was used, the average default recency that was used by participants in the first 50 trials. And as you can see, it seems to be pretty close to the optimal that is shown out here. So it does appear that participants generally tend to be starting all 3 task structures at recency values that are optimal across a very large number of 2-choice environments. Finally, we tested the second explanation of recency by correlating recency with working memory capacity. Here are our results, and overall what you need to know is that we did not find a very high and significant correlation. The highest correlation we found was between static environment and the symmetry span task, and overall the static task structure seemed to have the highest correlations. The others were pretty weak. We believe that this might be because in the gradual and the sudden task structures, the optimal recency values are pretty high, and therefore the cognitive load is pretty low overall. That is, here in the gradual and the sudden task structures, participants have to recall a lower number of previous outcomes, and therefore their working memories are not very taxed, and the recency is not very reflective of their working memory capacities. On the other hand, in a static task structure, a larger number of previous outcomes need to be included, and therefore here it is more reflective of the working memory capacities, and therefore shows a higher correlation. However, overall, we cannot say much about the role of the working memory limitations on recency, and therefore these results are inconclusive. Finally, we can conclude that people adjust recency adaptively to environment structure. Participants adapted their recency across task structures to achieve optimal values. They started at values that seemed to be generally optimal across a wide range of environments. They then adjusted recency to better values with experience in trials. Recency did not have conclusive correlations with working memory. Thank you for listening to the talk. Here are some useful GitHub links, which you can look at if you want to know more about this experiment and the study.